We now would like to analyze driven AC circuits with a voltage source. For example, in this case, we have a voltage source, which we denote by this symbol. We have a resistance, we have an inductor, and we have a capacitor. And what we'd like to do is find the current response in this circuit. So we'll begin with describing some functions for the alternating voltage source. So when we write our voltage source as a function of time, we'll write it as V naught sine of omega naught t, where omega is what we call the driving frequency. And that's, of course, when we write omega, it's always angular frequency. So for example, here, if we let this circuit now evolve in time, this blue dot represents the voltage. And you can see that as a function of time, the voltage source is oscillating between a positive value and a negative value, which is what the amplitude V naught is, because the sine function goes between plus and minus 1. Now, what we want to find in this circuit, our main goal is to find the current response. And that current response will have an amplitude which will be a function of the driving frequency. Also, because it's being driven, it's at the same sinusoidal function, but there's what we call a phase constant, which is also a function of the driving frequency. So I naught of omega is the amplitude, and phi of omega is what we call the phase constant. So for example, in this circuit, if we look at the current response and we let this go, at this point, the current and the voltage are pretty close to lining up. We can change the driving frequency so that we're driving this at a much lower angular frequency. And again, we can see the response. And now, notice that the magnitude of the voltage and the current are not lined up in time. They're not peaking at the same time. Here, the current is peaking in time before the voltage. And we can also look at other examples where we're driving it at an even faster, higher angular frequency. And in this case, you'll notice that the voltage amplitude is peaking before the current amplitude. And once again, we can see these oscillating voltage and current. So our main problem will be to figure out what these amplitudes are. And we'll look at circuits in a variety of configurations, where the various circuit elements are added in series or in parallel. This particular example is what we call a driven RLC circuit in series.